Okay, so finishing up section 4.2 is a very good, nice theorem we have called Rolle's theorem. And it has three conditions. If three conditions are verified, if you can verify three conditions, then something happens. So let's look. We have if the first condition is you have a function. If your function is continuous on a closed interval AB, two, f of x, your function is also differentiable on the open interval AB. And we say that because it doesn't necessarily need to be differentiable on the endpoints, okay? Because it's much something for the future to think about. Can it be differentiable on the endpoint? Three, f of A equals f of B, okay? If those three things exist, then we can say there exists a C belonging to the open interval AB. So that means C can't be one of your endpoints such that f prime of C equals 0. Okay. And I just wanted to show you pictorially what this theorem means. Okay. So here's a graph of a parabola, just something straightforward. And notice that it's a parabola and it's continuous on AB, the closed interval AB. And actually, now that I'm looking at this picture, I should have moved my B a little over. So let's do that. So B, yeah, let's put my B there. Okay. All right, that's a straight line. That's good. Okay. All right, so it's f of x. Our function is continuous on a closed interval. It's also differentiable, right? Because, and pictorially, what that means is you don't see any vertical asymptotes or sharp points or the cusp in your function, okay? So if I give you a graph and if you see that cusp or a sharp point or a vertical asymptote, then we have some differentiability issues, right? It's not differentiable, okay? And three, f of A equals f of B. In this example, f of A is 5 and f of B is 5, okay? So those three things exist. So by Rolle's theorem, that tells us that there must exist a C between A and B such that f prime of C equals 0. And we can see I labeled right there that C, right? And what you notice, C is also, it's a critical point, right? Because it's a local min, right? So, and I don't know if my stylus is not, okay, that's not bad. All right, so there's our f prime of C equals 0. All right, so that's all Rolle's theorem is saying. All right, so now we're going to do an example and make sure you pay attention carefully to this example. This is the only example I'm doing, but you will have Rolle's theorem to do for on your homework if you've already looked at it, which you should. All right, so here we need to verify Rolle's theorem for f of x equal x to the fourth minus x squared on -2 on the closed interval -2, 2. So again, what we're going to need to do is say if our function, we need to make sure our function is continuous on a closed interval, differentiable on an open, and f of A equals f of B. And then verifying Rolle's theorem, that means that there should exist a C in AB such that f prime of C is equal to 0. Well, if we do that, so that just means we need to take our derivative, set it equal to 0. If we get at least one value, at least one, you could get more than one, but if you get at least one value that the derivative equals 0, then you just verify Rolle's theorem. Okay, so let's go ahead and do that. All right, the first thing we want to notice is that, so in terms of our solution, notice that f is a polynomial. And there's a nice fact that all polynomials are continuous. I'm going to use CONT, that's the abbreviation, and differentiable. This is going to be my abbreviation for that, everywhere. All right, so that's a nice fact. Keep in your bank of definitions and facts and theorems in this class. And so because of that, and we're given this closed interval, so that just shows, since we have a polynomial, that shows that it's continuous on -2, 2, because if it's continuous and differentiable everywhere, then definitely on a small interval, -2, 2, then it's going to be continuous and differentiable. So, but you need to state that. If I ask you to verify on an exam quiz, you need to state if it's a continuous function. If it's not a continuous function, you need to state, well, it's discontinuous somewhere, but it's not on this closed interval. Because it can be discontinuous somewhere, but as long as it's not on the closed interval, you're good. You're still continuous and differentiable. And then you have to make sure it's also differentiable everywhere. So you would take the derivative. Okay, so we'll talk more about that. But here, this function is continuous everywhere and differentiable everywhere, because not only is the function a polynomial, when we take the derivative, it's also going to be a polynomial. Okay, so we're good there. The third thing we need to check to see is f of negative 2 equal to f of 2, right? Because that was that third condition. F of A has to equal f of B. All right, well, I'm going to leave it to you to do the work, but f of negative 2, I believe, should be 12. And we plug in f of 2, that also should give us 12, okay? So we just verified those three conditions. Now we need to show that there exists a C between negative 2 and 2, all right? So we need to still show there exists a C that belongs to negative 2 and 2, such that f prime of C equals 0. All right, so if f of x is x to the fourth minus x squared, then f prime of x will be what? This is a straightforward derivative, 4x cubed minus 2x, okay? And then we need to set f prime of 0 equal to, f prime of x equal to 0 and solve, okay? So we have 4x cubed minus 2x equals 0. What can we do here? What can we do? All right, so we can, Dr. Borman's pausing for a minute, so yes, very good. We can factor out a 2x. And so if we factor out a 2x, then we'll be left with what? 2x squared minus 1 equal to 0, okay? So that means 2x equals 0 or 2x squared minus 1 equals 0, okay? And right here, that says x equals 0, okay? Now, here's the thing. We actually, is 0, so is 0 a member, or let me say does 0 belong to the interval, open interval negative 2, 2, okay? And you know, if you need to verify, you can look on the number line. This is negative 2, this is 2. So this is our open interval. It's 0 in between this. Yes, of course, right? It actually separates our negative and positive numbers. So 0's there. So that means we just answered the problem. So we actually, if we wanted to, and feel free, and I think in your book when you read the section, they saw for it, that's fine. But we just need to show there exists. So as long there exists one, we don't need to show all of them. I could ask you for that, but here we just need to show that there exists. So we actually can stop here because since 0 belongs to negative 2, 2, f prime of 0 equals 0. Thus, Rolle's theorem is verified. Okay. And just keep in mind, it's verified not just because f prime of 0 equals 0 because we found a 0 in between that interval, but also those three conditions were satisfied. F of x was continuous on a closed interval, it was differentiable on an open, and f of a equals f of b. So you have to verify those three things first, and then take the derivative and set equal to 0. Now this is what I'm going to end on, is that let's say that say that 0 wasn't on the interval, and you don't have to write this down. I just want you to know. Let's say we were on the interval from 1 to 2. Okay. Well, 0 isn't in the interval 1 to 2, so then you would have to finish solving for that, which is not hard to solve for that. Add 1, divide by 2, and take the square root to see. Okay. So you have to. It's just, I want to emphasize, you have to make sure that there exists a number in that interval such that f prime of that number equals 0. And once you do that, then you have verified Rolle's theorem, And I am done with the notes. Okay, so all the best on that take-home quiz.